Okay, so hey guys. Today we're going to talk about type inferences, and we're going to be solving certain problems that relate to finding the correct type for certain expressions, and we'll be probably talking more about some of the type problems in the homework if we have time. So before we get into the section of problems, I just want to quickly review basically like how an expression has a type and how you can deduce the type of an expression from the greater equation. So we can start with the basics really quickly. So here, if I were to give you an equation such as just a plus 5 equals, let's say, 9, right? What would you expect a to be?
An integer.
Yeah, an integer and 4, right? But the more important part is that the fact that a is an integer of type int. So we can use this simple logic to deduce the types of multiple variables. For example, the one given in the section notes here is, or in the lecture notes I should say, is this. Lambda a, lambda b, lambda c, where if a b plus 1, then b else c. So here we have the variables a, b, and c. And here we can see, by immediately looking at the equation, that we have a b plus 1 in there. So this tells us that b is a integer, right? So what we can do now here is, instead of writing the whole equation, I'm just going to write this part. We can have something for a, I should write it pretty, something for a that we're not going to write yet, and then something for b, which we just deduced that it's an integer, right? Because it's b plus 1, you can only add integers with integers, not booleans, or any other types of types. And then we have period, lambda c of some other type. So now we need to deduce the type of a and c. Here we can see that we have an if expression that we know that by if expressions you need to have a boolean here, right? So the thing here at the end, right, a parentheses b plus 1, whatever this evaluates to, it must evaluate to something of type boolean, right? Okay, so once we have that, we can see, okay, then b else c. The thing is with if and else, if then else expressions, the type of the variables that are returned in the then case and the else case must be the same. And we've deduced the fact that b is an integer, right? So what type will c need to be? Also an integer. Great. So we've got the type of b and c. Now that we have that, the only type that we don't know still is the type of a. So here we see that a, we can look at a, b plus 1 in this context. A, again, b plus 1. Do you remember the application, like semantics, where we have E1 and E2, and we apply E2 to E1, right? Yeah. So, yeah. How many types of expressions do we have? We have like the variable itself, right? Let's say an x, and then we have lambda a, let's say b, lambda a, and then we have E1 and E2, where we can combine expressions, or we can apply one expression into another, right? Where E2 is applied to E1. This is the same logic here. Here we expect b plus 1 to be applied to a. Then we should be able to see that a here is a function, right? So a takes in something and then outputs something else. And these two things might or might not be different types.
So in this case, it would take in an int and map it to boolean?
Exactly. And how did you come up with that?
Because you're applying a to, or like a to the argument. The argument we know is int.
You're applying, yeah, you're applying the argument to a.
Sure.
Yeah. No worries, it's okay.
Okay, cool. You're applying the argument to the function, and the argument is an int because, as we already talked about, and then we also stated earlier that the output or the results of this application should be a boolean because it's a condition within the if statement.
Exactly. So, and how many inputs, how many types will A have? If it's a function, will it have more than 2 types, or will it just have 2 types, where you give it int and then output boolean?
Just 2.
Just 2? How do you know that? So there can be functions that take in, let's say, type of something, and then they might take another input, and then they might produce like a final type. How do you know that this expression right here only takes in 1 input and outputs a type?
So in this case, there's only 1 argument, and that entire expression needs to evaluate to boolean. So
Exactly.
that's complete.
Exactly. For it to be well typed, it needs to be exactly like you said. Take in 1 input and then output to a boolean. So then how would we write this if it expects an int and then it needs to produce a boolean at the end? Exactly. Int, arrow, bool, right? That's a shortcut. Yeah, perfect. That's it. That's how you deduce types of variables and expressions. So this was a simple example. We will now look at more complex examples, as well as defining a new typing relation that we'll be using for this section. Can I erase this? Yeah. Okay. It's a bad eraser. Okay. That's a shame. Okay. So let me write this. So here I'm going to define a new typing relation. So we have gamma, right? What do you remember what gamma was?
Is it the context?
Yes.
Okay.
Yeah.
As in like
Or
all of the
yeah.
variable types that kind of exist.
Exactly. So the context will have exactly all the possible types that will exist, and we write that as gamma. So a Greek letter gamma, capital, and then this is the symbol we use to say, okay, this expression will be under this context. So we can write E, and then tau, that stands for type, and then here I will draw a triangle and the letter C. So you're familiar with this part, but what is this part? This part here says that that there's an expression of type of E that has type tau, provided that every constraint in the set C is satisfied. So here C is the set of constraints that we are applying to this equation, and these constraints in the set of constraints can be expressed as tau1 congruent to tau2, where we will have different variables actually denoting types, and we'll be indicating that these types are congruent to each other or not congruent to each other. Yeah, and the way that we define this entire expression is through inference rules and axioms again, what we've been doing since the beginning of the class. So if I were to give a simple example, sometimes we might have constraints that are just empty. So let's say I have this simple example right here. We have a variable of type x. We have a variable b of type y, where we have the expression just 2, which is of type int, with the constraint set C. So here, we're not using the variable a in our expression right here, right? 2. Our expression here is just this, 2. I just gave these variables for extra, but we're saying that there might be these variables a and b of type x and y. And the expression that we have is of type int, with a set of constraints. In this case here, since we're not utilizing the variables a and b, we have no constraints. We don't need to constrain to anything. So here, our set of constraints will actually be equal to the empty set, right? But if I were to give this example, again, A is of type X, B is of type Y, where we have the expression B plus 3. And this whole expression right here will evaluate to type int. Right? And then we have our set of constraints. So, B plus 3. We know that the variable A is of type X, the variable B is of type Y. And we have the expression B plus 3, which needs to, at the end, evaluate to an integer. What does this tell you about the type that B is? What is Y equal to? Which is the type of B? Int. Exactly. So that's a constraint. And the way we indicate this constraint is by saying C is equal to the set B, or sorry, Y is equivalent to the type integer. So that's it. Yeah. So in homework problems and like I guess now the final, when you're asked a question about the set of constraints, like you need to be able to look at the variables that exist inside the equation and be able to deduce, okay, this is an integer, this is a bool, this is of type function. Cool. So now that we have those basics down, we can start on the section problems. Yeah, so are there any questions? Do you have this? Okay, cool. Okay, we don't need to erase this. Cool. Yes. So again, we need to, for these questions that we're about to do now, this is the constraint-based typing judgment. This is how we express it. Context gamma, expression E. The expression E evaluates to, is of type tau at the end, and it might be constrained by the set of constraints labeled as C. So we'll now be giving inference rules for products and sums for certain expressions. So we can start with the first expression, one where we have E1 comma E2. Do you know the name of this right here? What would you call this as?
Product.
Yeah, a product. Exactly. Yeah, just checking. Or actually, more than a product, it's actually a pair.
Okay.
Yeah, it's actually a pair. So you would call this a pair, or in normal CS speak, like a tuple, right?
Yeah.
Yeah. So we need to define the constraint-based typing judgment of E1 and E2 using inference rules and axioms. So we need one inference rule that lays out the conditions there needs to be for the pair E1 and E2 to be of certain types. So as I said, we'll be writing an inference rule, and it will be something like this, right? We'll have our conditions, and then we'll have the part where if our conditions are true, then this reality is true. So let's start with E1. If I want to define the constraint-based typing judgment of E1 with this equation, what would I write? Right? So E1 and E2 can be of any types, right? But I need to express this in a formal context. How would you start this? So I need to have two conditions here at the top for E1 and E2 to have its own inference rule. How would you start it?
I guess you would write that typing judgment for both E1 and E2 separately?
Yeah, exactly. So to write that for E1, we just literally copy this. Gamma, again, this is the context, right? For all the context that exists in your set, where you have the expression E1, it needs to be of type tau1 under the constraint set C1. Yeah. Oh, we need to make this line a lot bigger. So that's one condition. And then we need to do the same thing for E2 as well, because it's a pair. So again, for your context, gamma E2 of type tau2 This needs to be under the constraint set C2. So far, have I said anything about the fact that tau 1 and tau 2 can or cannot be equal, and C1 and C2 can or cannot be equal? No. So what is this telling you so far? Like it should be telling you the fact that T1 and T2 can be equal, but they don't need to be. And that the constraint set 1 and constraint set 2 need to be equal. They don't need to be. We don't know that yet. But now that we've established these conditions, we can define the constraint-based typing judgment for the pair E1 and E2. What do you know about pairs? Can these be of different types?
Pairs?
Mm-hmm.
In products, yeah, they can be.
Yeah. They don't need to be though, right?
Or sorry, yeah, they don't need to be.
Or it is, yeah. So the way that you would express the type of E1 comma E2 in a pair would be like this, where let's say you have type tau 1 for E1, right? Product or cross tau 2. But if E1 has type tau 1 and E2 has type tau 2, then this pair must have the type tau 1 cross type 2, right? Cool. So we need to express that in a formal context. And the way we do that is, again, under the same context that E1 and E2 were, where we have the pair E1, comma E2, which must be of type tau 1 cross tau 2. This is the important part for this section. We need to define what constraints this pair will be on. So if E1 is under constraint 1, C1, and if E2 is with the constraint set C2, what does the pair E1, E2 need to be under the union? So why? So why would it be the union? Why would it not be, like, let's say, the intersection or the union?
Yeah, if tau 1 is subject to, or I guess the first type is subject to a certain set of constraints,
Mm-hmm.
and then the second element in the pair is also subject to a certain set of constraints,
Yeah.
then when you're looking at the type for the entire pair, it should be subject to all of those constraints for individual elements.
Exactly. Exactly. Yeah. So then we would say, yes, that the pair E1 and E2 are subject to the union of the constraints of C1 and C2 because all those constraints need to exist for E1 and E2 to be in a pair. Yeah. Union C2. Yeah, and this is it. This is the inference rule for the pair E1 and E2. So that was pretty easy, right? Because you logicked out the fact that for them to be together, they need to be under the union, the same constraints together. Cool. Okay, so let's get into now more interesting problems. Okay. Cool. Okay. 2. We have the expression hashtag 1E. I will call this a hashtag. Or a pound sign. Sure. But we're in 2019, so hashtag. What does this operation do? Do you know?
That extracts the first element of the pair.
Exactly, but what does E need to be?
Or sorry, first element of B and E should be a pair.
Yeah, exactly. E1 and E2, right?
Yeah.
It could be, so far in our language, did we define pairs that have more than 2 elements? Or 2 expressions?
I don't think so.
Yeah, we didn't, yeah. But like if we were to define different expressions, right, that could be possible. So then in this context, we need to keep in mind that will be equaling a pair E1, E2, right? So this is important because this is how we're going to define our inference rule for this expression. Okay, so we are given E. What do we need to know about E before anything when we're writing our inference rule? What will our condition need to be? So we need to define a formal expression.
It needs to be a pair, so that would be something cross
Mm-hmm. So we don't need to define that yet, actually. We just need to state what constraints E is under, right?
Okay.
So
Constraints of its individual
No, just E itself as a pair. Because,
Oh, sorry.
yeah. So the way we would do that would be gamma E, which is of type tau. And tau can equal x cross y, right? Or int cross int, bool cross bool, under constraint set C. So here we're still thinking abstract, right? Because what you just said, the fact that we need to define E as a pair, there are other inference rules that take care of that. The beauty of these inference rules is that, yeah, you can go down, and you only need to be dealing in certain abstraction levels. Yes. So this is what E needs to be under for hashtag 1E to be defined properly. So now, if E is under the constraint set C and has type tau in the context gamma, then hashtag 1E will have, now we need to be careful here, it will have a certain type. So the hashtag 1E returns just one element, right, in the pair E1, E2. We need to have a variable that can be of any type. But it just needs to be like one type. That type could be equal to int, or it could equal int goes to int, right? So the way that we would define the type of hashtag 1E now is not tau, but with a variable such as capital X, right? Because here again, we are leaving the possibility that X can equal any types and any combination of types, right? It could be a function. So now that we've said that, we need to define the constraint set that it is under. So hashtag 1E is still under the constraint set C. However, we now have new conditions that we need to make sure are correct. So this is exactly where we will be showing the fact that E is actually E1, E2. So how did we define the type E1 of the pair E1 and E2 again?
It'd be the type of E1 cross type of E2.
Yeah, so how could you say that? Just like if you were to use variables X and Y.
So it would be X cross Y.
X cross Y, yeah.
How would be equivalent to X cross Y?
Exactly, exactly. So now we would be unioning that with this. Yeah. Tau is equal to X cross Y. Yes. This is the constraint for pound 1E, or the first element of E. Yeah. So this makes sense, right? Yeah. But we're forgetting one thing that we need to state. What do we need to have? What do we need to know about X and Y? Yeah. Like they need to be of certain type of variables.
Can they only be, or they need to correspond to?
It's okay, no worries. The constraint that we need to give here is the fact that X and Y need to be fresh variables. Fresh variables, yeah. Fresh variables meaning X and Y are unique types that might or might not be equal to other certain types that might pop up. So we just need to note the fact that X and Y are, you can just say fresh for fresh variables. Yeah, they're fresh, they're new. Yeah. So this is for pound 1E. What if I were to do 2 instead of 1 here?
It'd be the exact same thing, would that be Y?
Exactly, yeah. So if I were to just do that here as well, 2E would be Y. Exactly. Same thing. Yeah. Yeah. The only thing that changes here is the fact that, okay, now this used to be type Y. Cool. Okay, so this is getting pretty repetitive. We can get to more interesting problems. Yeah. So now we're going to be actually doing a pretty complex equation where we'll be figuring out the types of different elements. So this is the equation. So instead of gamma, if we know that our context, actually, no. So we're still going to be defining this under a given context, just for clarity's sake. So under the context gamma, we have the variable x. That is of type A. And then we have the variable y. That is of type B. Where now we start to write our expression. Pound 1e. Or sorry, pound 1 y plus the expression x, this second element of y, plus sub-expression x plus 2, which needs to be of type tau at the end, this whole expression right here, starting from here to here, under constraint set C. So this is not simple, right? Yeah. it's not as simple as, let's say, b plus 2 is. Yeah. So we need to figure out the constraint set C and tau t. So immediately looking at it, it's like a mumbo jumbo, but the way that we should approach this problem is by looking at certain cases that will definitively tell what certain types are. So do you see any definitive examples that will make us think, okay, this variable right here, y, must be of type x, let's say,
Yeah.
type y. Okay, so give me some.
Like, it should be a pair.
Which one?
Or I guess that's not very helpful, but y should be a pair.
Okay, so yeah, so first observation, y is a pair.
Because we access like the first and second element.
Exactly, yeah.
And x is an integer because it's x plus 2.
Yeah. Thanks for pointing that. Actually, it's not supposed to be in. There's a plus there. Yeah.
Oh, it's not a plus, sorry.
No, there's
Oh,
no
is that
plus there.
application?
Yes.
Okay, in which case x should be a function.
Exactly.
Or, an abstraction, I guess.
Yeah. X is function abstraction. Let's just write function for clarity's sake. Okay. But you still haven't said anything about the types of x and y. What a and b might be equal to. So the way we can approach this is by just defining these abstract types that we don't know what they are yet, but we'll be constraining what a and b could possibly be.
Okay.
From the set of any and every single type to these given types right here.
Okay.
Yeah. So you have said that y is a pair, right? What is the type of a pair? What can it be?
Call it like big X plus big Y.
Exactly. So then we can just here write, let's say, right, and the type of y we know definitely is b, right?
Yeah.
So b you said is equal to x cross y. Great. Oh, sorry. X cross y.
In what cases do we use equals and other cases do we use equals?
In this case, thank you. You should be using congruency. Yes. You only use equals when the number is definitely equal to that. This is, we are saying that it is congruent to it. Yeah. Thank you for, or equivalent to it. Yeah, thank you. Cool. So b can be of type x cross y. Okay, here we are using y again. And we're getting the second element of y. So then how could we indicate the type of y here?
Still X cross Y is fine.
Actually, no, it's not, right? Because what did we do earlier in the previous problem? We said that when we get the first or second element of the pair y, or pair e, we need to ensure that those two types are fresh variables.
Okay.
Yeah. Fresh variables meaning they need to be unique at first.
Right.
So at the end, obviously, the variable y will need to have the exact same type for wherever it's written.
Okay.
However, when we're defining our set of constraints, we need to start with the notion that it can be different types, actually. So,
Cross V or something.
say that again?
U cross V.
U cross v, yeah. So u and v look very similar to each other. So let's just write z,
Or Z and whatever. Yeah,
z and w, yeah,
Z and W.
sure. Z cross w. Here, right here, okay. And you said something about the type of x, right? What will x be?
So x takes in, so we can see from the last term that x is, so first of all, we know x is a function, so it's something to something, something arrow something.
Yeah.
The first something, which is the argument, should be an int, because that's what we see from the last term. So
Yeah.
x, which is type A, so I guess A is equivalent to int, arrow, something.
Yeah. Yeah, exactly. To say that in a more formal context where we indicate all the possible different types, here we see x being applied with the second element of y,
Yeah.
and here, yeah,
Sorry, go for it.
yeah. So, and here we see x applied. Here we see x where its input is just 2. So if we were to go off of this example right here, just x and then e2 being pound 2y, this context here, or here, let me just start numbering these. 1, 1, and then 2, 2. Yes, so our third case where we could deduce something, right here's 3, is where, yeah, where we, exactly. So the way that that would be written is, let's say the type of x, which is a, right, so a. So say that again.
Is equivalent to w, arrow,
Sure.
variable, right?
Yeah, exactly. It needs to be u. Exactly. It needs to be a fresh variable. Yes. So cool. And we see here x again, and we need to use fresh variables.
Okay.
So what we define in this case here is we know that 2 is of type integer. So we didn't use any other variables to indicate that type. It's just int goes to another fresh variable. So let's call that v. Okay, and this is for fourth finding. Yeah. So we're getting there, but not quite. We're still not there. No worries, yeah.
So for number 4, would we also say A is equivalent to that?
For number 4, would you say that? Yeah, thank you. Yeah, thank you so much. Okay. Okay. So we have 4 cases where we've deduced the types of elements, but we still do not definitively know what A and B are. So we need to look deeper. You see these additions right here, right?
Right.
Yeah. So what do these additions tell you? What can you add? What are you allowed to add only in our current context?
Integers.
Integers. So what does this situation here tell you? Pound 1 y plus something.
I mean, pound 1y should be an integer.
Exactly, overall, right? So then what? How can we connect this to what we already have?
We say x is an integer.
Exactly, exactly, exactly. So then I will write 5 here. This is readable, right?
Yeah.
Okay. Exactly, here we have x, because this is the first element of y. And now we say x must be of type int. Yeah, or it's congruent to type int. Okay, similarly, let's look at this addition right here. Let's start with the easier example. 2 is applied to x, right? What does this tell you about x2?
That should also be an integer.
Yeah, the result of applying 2 to x, right? Yeah, the application, exactly. So how could I?
That would be v.
V?
Would also be equivalent to an integer.
Exactly, cool. Okay, we're getting there. Yes, yes. So there's one more finding that we can make by utilizing either this or this plus about this whole expression right here.
Yeah, so,
What would that be?
oh, okay, so we see, based off number 3,
Mm-hmm.
yeah, number 3, u is the result of that application, so that should also be an int.
An int, exactly. So u here is the result of this, right?
Yeah.
This expression right here. So x parentheses, pound 2y, close parentheses, takes in an expression of type w, and outputs something of type u, right? And looking at the two pluses here, we can see that u must be an integer at the end, right? Cool. 7. Let's just say 7 right here. U is of type int. Okay, exactly. So you see all these constraints right here that we've defined. There are no other constraints that we can make. So then we would define the set of our constraints as these, basically. Yeah. So obviously, when you're writing in the homework, right, I guess I wrote it very informally. So what you would do is just like b is equivalent to x cross y, comma, b is equivalent to, right, z cross y, comma. Yeah, but this is our set of constraints. Yes?
I was just curious, is there any reason why we can't just directly say A is equivalent to W arrow int, if we know U must be int?
Yeah. So that's a pretty good question. The thing is, here we have, from just our findings here, we don't know if, we haven't done the process where we now reason out, okay, so if x is an integer and if y is an element, but at the end we're adding the second element of y, then y must be an integer as well, right? We haven't done that reasoning yet. This is just to write our findings where, again, like it's called a unify algorithm, actually, yeah. Yeah. There's actually a process in this lecture that this section is tied to that is dealing with unification, where we're defining type substitutions, right? We'll be substituting in types. To answer your question again, we haven't done any type substitution here yet.
Okay.
As you can see, we have defined the type of b twice, right? Where it's x cross y and then z cross w. It's pretty redundant. What would you do if you were to substitute it? You would just get rid of one of these, right?
Yeah.
Or even better than getting rid of one of them. Yeah. Yeah, even better getting rid of just one of them. Get rid of one of them first, and then replace x cross y with int cross int, right? So you will be type substituting until we reach the final state of type substitution. It's just like processing expressions. Now you're processing types with the unify algorithm. And that's actually what the third question is. The third question of this problem asks you to utilize the unify algorithm that is given in the lecture notes to end up with the final set of constraints. However, the simple version of you doing the unify algorithm is just reasoning it out by yourself manually. So we already know that x is of type int, right? We know that v is of type int, and then we know that u is of type int. So now we can actually reason out the type of b and the type of a here. So how would you do that? And we can reason out the type of a here as well. Like just shoot some of the types off to me right now.
B is an int, so A is now, instead of int arrow B is int arrow int.
Yeah. So let me just say the unified C. Yes. So say that again.
So, for example, A is int arrow B, so that since B is int, then we can just do int arrow int.
Exactly. So then here what we would have is exactly, it's indicated as such with these arrows. Int going to int. Exactly, comma. So that's one.
Yeah.
What else?
So that means W and U must be ints. I guess we don't really need to write that.
We should write them. Yeah, because we have defined these. So actually what you're doing, like you're skipping a few steps, right?
Oh, should we go step by step?
Yeah, we should go step by step. It's okay. Where we're defining, okay, if A is equal to the type int going to V, then W must be of type int.
Yeah.
And and here you would replace with int. That's how you arrive at it, right? Which is fun. We can just say all the combinations. There are 1, 2, 3, 4, 5, 6, 7, 8 of them, where you define all the types that we've defined. So we can go by alphabetically. Okay, if A is int going to int, what is B?
B would be, I guess let's use
Mm-hmm.
W.
Sure.
So, and then W we know is int from 3.
Yes.
And then we also know Z is the same thing as X,
Yes.
which is an int. So that's also int process.
Yes. Exactly. That's
Sorry,
A and B. Yeah.
Sorry, this is int cross it.
Int cross it. Yes. Exactly. Yeah. So here then what our finding says is that X is a function that takes of type int and produces type int, and then B is actually a pair, a tuple, whatever you name it, that's of type int and int. So now all there's left is to just write out the types that all the other different fresh variables that we've defined. So what would the type of X is again? What is the type of X again? Int. Yeah, it's just int. Yeah. So.
Okay, so we can't drop in.
No, because here you're utilizing the unify algorithm, which I could go through, but it's pretty boring. It's in the lecture notes for type inference. Yeah. And then we have here y again, type int. Yes. And then we have z here, type int. Yes, z, w, u, v. Yeah. Exactly. Of type int. U going to type int. Exactly. And then v going to type int. Yeah. Comma, comma. Yes. Cool. So then this would be the set of our unified constraints right here. Yeah. So this is the set of constraints that is not unified, and this is the set of constraints that is unified. And the only difference is that here we haven't done any substitution, and here we have done substitution to the max. Yes. Yeah. That pretty much actually finishes this section. So it's up to you now what we would like to do. We could do more complex equations where we're creating new expressions and then finding that type. Do you have any questions, any general questions?
I guess when would we use, is there a difference between tau and using a letter? I guess
Yeah.
Convention-wise, tau is a little more general, while the letters are not always, but usually a specific, an int or something.
Yes, that's pretty much it. Tau is usually just used to express any type of any type without kind of referring to its fresh state, right? Whereas if you were to use x and y, you would be saying okay, x and y are of different types, and just also because of convention as well, but also because of the fact that you want to differentiate these types, and you usually wouldn't want to be utilizing the type tau as well as x at the same time, right? Because then you're kind of violating exactly the convention standards. Yeah, that's one. Let me see here. Yeah, so let me ask you a question actually. Do you realize, do you know the reason why we kept emphasizing the fact that, let's say, x is a free variable, a fresh free variable, and y is a fresh variable, and etc.? Do you know the reason for that? No? So we do that because we would like to avoid what's called a cyclic substitution, where you have the same type go into its counterpart. So you don't have cases where it's x, let's say, goes to type y, and then let's say z, right? This is let's say a certain function. If you don't indicate the fact that x and y and z are fresh variables, it is entirely possible for you to have this situation right here. X going to x going to x. So this is a cyclic substitution right here. This would not end. This would keep going in an infinite loop. And the fact that we're only dealing with finite types here, having cyclic substitutions here doesn't make sense. And the unify algorithm that is actually given, which I will pull up right now, the unify algorithm that is given is designed to always terminate. As in, when you theoretically run the unify algorithm, you will always end up with types for a certain equation. Sorry. Yes, here it is. So this is the unify algorithm. Yeah. So if you are given a set of constraints where the set is the empty set, then you have the empty substitution, as in, okay, there are no constraints. However, now, let's say you are given C, where C is these type declarations right here, you'd be running through this equation. So you have type tau and then tau prime. If you see that, let's say tau is int, right? And then you have another tau type, which is also int, you call unify on not this element right here, but you call unify on the C itself. And then you just progress down, where, as you can see, there are different cases that take care of different situations. And then at the else case, you have fail. Fail would only be called if you have kind of illegal type declarations, or if it's basically not stated correctly. And this, again, the specialty of this unify algorithm is that it is always designed to terminate. So you'll never have infinite running loops. But if you were to have cyclic substitutions, if you have the possibility of cyclic substitutions, then you cannot guarantee the fact that the unify algorithm will terminate. Yeah. Yes. And I guess one thing I can also talk about is kind of the formal definition of substitution of types. So where could I write that here? I can turn this board over, right? Yeah. Cool. Yeah. So just for clarity's sake, I'm going to define what exactly substitution of types are. So we have our store sigma, right? And we are given a type X, let's say. And yes, here we have two possibilities. Either the type X in store sigma is equal to tau, with the condition that if X is of type tau, which is in sigma. Yep. Or we leave it as X. Tau, actually, yeah, to answer your original question, we here are representing tau to mean either an integer or a Boolean, like a definite type, right? Not like Y or Z. Yeah. Or we leave it as X if X isn't in domain of sigma. Yeah. So the unify algorithm that is right here is running off of this substitution. But let's say if the substitution, or if sigma is given the input integer, then you return the same integer type. And if you're actually given a type for a function, so let's say tau going to tau prime, then you would actually be breaking these down into two parts. Yeah. So this part here is actually pretty intuitive, right? Because you'd be doing substitution on not on this function altogether, but you'd be breaking it into two parts where you first figure out the type of tau, and then figure out the type of tau prime. Yeah. Cool. Yeah. Yeah. Other than that, do you have any other questions? Nope. Okay. Then we can end section early here, actually. Yeah. Thank you guys for joining in. Have a great weekend. Bye-bye.